Hi, and welcome back to our lecture series on computational finance. In this short video, I want to explain to you some basics of numerical analysis that we will be using every now and then throughout our lecture. And we'll start with a very simple example of what could actually go wrong when using a computer to solve very simple tasks and doing some very simple calculations, actually. And this, of course, can happen in any context, but we'll later on see that this might actually happen in some specific contexts of with a financial background. We'll start with the representation of numbers in a computer. Now, we as humans, we work in the decimal system. We have 10 digits on our hands. That's why we are using the decimal system. So if, for example, we want to write 1492, we think of this as 1000 plus 4 times 100 plus 9 times 10 plus 2 times 10 taken to the power of 0, which gives us 2. Now, decimal places can also be depicted in this manner. So, for example, 0.42 is equal to 4 times 10 taken to the power of minus 1 plus 2 times the 10 taken to the power of minus 2. Now, in the decimal system, you might have seen this in high school. Some numbers actually do not have a finite representation. For example, 1/3 is 0.33333 and so on until infinity. That's why some numbers cannot be represented in a finite manner in the decimal system. Now, on a computer, in contrast, computers use the binary system, and as a result, we have to switch from the decimal system, for example, 21.5, to the binary system, which in this case would give us 2 taken to the power of 4 plus 2 taken to the power of 2 plus 2 taken to the power of 0 plus 2 taken to the power of minus 1. And thus we have 10101.1, and this would give us 21.5. Now, this conversion from the decimal system to the binary number system can lead to some problems, because there are numbers that can no longer be written in with a finite representation. For example, 7 over 10, 0.7, has a finite representation in the decimal system, but actually an infinite representation in the binary system. And as there is only a finite amount of decimal places for the number representation in a computer, the computer can only work with a certain number of decimals, the representation of such a seemingly nice number in the decimal system, however, in the binary number system, has an infinite representation and needs to be cut off from a certain decimal, and the number needs to be rounded. So even just writing a number like 0.7 on a computer will lead to a rounding error, and this is actually what happened in MATLAB in one of the previous videos. Now, that's a very simple example where we immediately get a rounding error when we are using numbers on a computer. At the same time, of course, there are more complex mathematical terms that are given as an infinite sum. And these also need to be made calculable for the computer. For example, the exponential function is an infinite series, and when we calculate this sum through a computer, we need to cut off the infinite sum at some point, and you will get what we call a truncation error. We have to truncate this infinite sum after a certain amount of elements, and thus we get a truncation error. Next, we also observe the phenomenon of so-called cancellation. This describes the loss of accuracy due to the subtraction of almost equally big floating point numbers. So if we take, for example, A and B, 2.345678, and B, 2.346789, the difference is actually rather small, and we are expecting the solution to be 0.001111. But if we only calculate with 2 places of exactness with 2 decimals, we would actually get the solution a minus b equals 0. And this will give us an error. Problem is, the absolute error does not seem to be very big at first. That's just the difference between 0.001111 minus 0. So actually the difference b minus a is also the error. But the cancellation of leading places results in a disproportionately high relative error. So actually we are expecting 0 and we get 0.00111, so the relative error is extremely high. So these are some problems that we might encounter when working with computers and with calculations, finite representations of numbers on computers, etc. Now, moving on to numerical problems and algorithms, we will be looking for certain properties of problems and algorithms. We start with stability, then we are looking for convergence in our algorithms, and we are looking at the condition of numerical problems, which doesn't really have anything to do with the algorithms we are using, but the condition is related to the mathematical problems themselves, and you'll shortly see what these are all about. Let's shortly talk about these. First, we start with stability. Now, we consider a numerical problem as a function f that uses input data x and produces an output y. First, the actual input data might be disturbed. So there is an error, delta x, that goes into our input data, and we are actually not working with x, the true input data here, but we are actually working with x plus a disturbance or an input data error, and thus we only can use x bar. Now, the exact solution of the problem with the disturbed input data is given by f of x bar. We are not trying to get y, the true solution, because this would mean that we are using different input and we are still arriving at the true output for x and not x bar. So we are expecting f of x bar. And an algorithm, however, will provide a solution y star. So when is an algorithm stable? We will call an algorithm stable if the relative error, this is the output we are expecting, given that we are using disturbed data, f of x bar, minus the actual output. We take the norm of this difference, so basically an error metric, relative to what we were expecting, given that the input data is disturbed. And if this relative error has the same order of magnitude as the machine epsilon, then we call the algorithm stable. So in essence, we have disturbed input data, and the relative error caused by this input data isn't amplified by the algorithm when it comes to the output. And the order of magnitude is meant to have the same order as the machine epsilon. And what is the machine epsilon? Well, if we take x, the true data x, if we round it on the computer, and we again look at the relative rounding error, this has to be smaller or equal than a fixed parameter of your particular computer, and this is called the machine epsilon. So this is actually the precision with which you are working on your respective computer, and you can just look that up actually depending on what kind of expensive computer you're using. If you have a cheap notebook, probably the machine epsilon will be different than if you're using a high performance computer for high performance computing. Next, let's look at the condition of a mathematical problem. Now, ideally, the error in the output data due to disturbed input data should not become too big, and this characterizes well-conditioned problems. The following relation is defining what we call later on the condition. We have the norm of x minus the disturbed input data x bar relative to the true data. So this is the relative input data error times a constant sigma, and if this is larger or equal, then the true solution for the true input data f of x minus the true output, given that the input data is disturbed, relative to the true solution with the true input data, again taken as norms. Then, if this is valid for a numerical problem with the relevant norm given here, then this number sigma is called the condition number of the problem. And it means that actually the error you are expecting, given that you're using the true or disturbed input data, is amplified only by a certain constant sigma, the condition number, given that we already have an error in the input data. So this characterizes well-conditioned problems if sigma stays relatively low. Obviously, we want the sigma to be rather low. To give you an example of the condition of a mathematical problem, and it's important to stress that this property does not depend on the algorithm we are using, let's have a look at this polynomial in the monomial form, with the monomial representation of order 8. We set it equal to 0, and we now solve for the roots of the polynomial using the standard MATLAB function roots. So we get as an answer, first of all, we write down the vector of coefficients. We start out at 1, so this is for x taken to the 8th power minus 36, etc. This is P1. We solve for the roots of P1, and as an answer we get 1, 2, 3, 4, 5, 6, 7, 8. And again, we only give out 4 decimal places here, so we probably have some rounding errors at later decimal places. And you can imagine that this polynomial was actually created in such a way so that it has the roots 1, 2, 3, 4, 5, 6, 7, 8. So these 8 roots, those are exact, the exact solution to this equation. Now let's change one of the coefficients just slightly. So we introduce a very, very small error here. It's very tiny, and now solve again for the roots. And as you can see, 1, 2, 2.99, 4.16, 4.57, we suddenly get 2 complex numbers, and we end up with 8.2726. So a very small disturbance in the second coefficient throws MATLAB completely off, and we have a huge error in our solution. Now we can see that the small error in the input data strongly influences the quality of the solution. And this is actually not a characteristic of the function roots. It would happen with any other algorithm as well, but a result of the bad condition of the roots calculation of a polynomial given in the monomial representation. We will later on see that we can solve this problem by switching the basis. Polynomials form a linear space, a vector space, and by switching to another type of basis, for example Chebyshev polynomials, the problem is solved to some extent. So the condition is much, much better, and we can then solve this in a much better way. We've also seen that actually 2 of the solutions here are complex numbers, as indicated with the addition of the imaginary unit here. So for those of you who don't know what complex numbers are and who haven't seen complex numbers before, let's just go through complex numbers. We look at the fields of the squared real plane, real 2 tuples, and define for 2 numbers a, b, and c, d, first of all an addition, first element plus first element, second element plus second element, and also a multiplication. AB times CD is giving us as a result AC minus BD and AD plus CB. Now these operations give us actually a field of numbers, first of all, in which every number except 0, 0 is invertible. So this field is called the field of complex numbers, and we write it with this double C. Complex numbers are usually written not as A, B, C, D, but actually as A, B equals A, the real unit, plus I, the imaginary unit defined as 0, 1, times B. So A plus I times B. Quite interesting characteristics of the complex numbers. This is all coming from complex analysis and complex calculus, function theory. If you take the imaginary unit and square it, you actually get -1 in the real numbers. You can easily show that the complex numbers encompass all of the real numbers. So it's a true subset. And the fundamental theorem of algebra tells us that every polynomial of level n, of degree n, has n complex roots. Now in the real numbers, this isn't true. For example, x squared plus 1 equals 0 is not solvable in the real numbers, but in the complex numbers, we get as a solution I. So the imaginary unit, this is what we call I. And these two solutions here we got from roots. Those are two complex numbers. So actually what happens is we don't even just have rather large errors, for example, here and with 8, but in line 6 and 7, MATLAB actually leaves the real numbers and gives us two complex solutions for our initial problem. So we are not just off when it comes to errors, we're actually leaving the real numbers altogether. Okay. Next, we are looking for convergence and complexity of algorithms. Now, many mathematical problems can only be solved iteratively. That is, we are trying out one solution, then we improve on that and again improve on that in the next step. And after, let's say, 10, 15, maybe 100 steps, we arrive at a final solution we believe to be best. So given approximate solution xn, we try to improve on this in the next step, xn plus 1, and so on. And obviously we hope for this sequence of solutions, x1, x2, x3, so on, to converge. So the limit of xn should converge to x star. Then the question is, of course, we do need to, we require the sequence to converge. But the question is, how fast will it converge? It could converge like this. So we are using a lot of steps here, or it could go like this. And we're done. That's the order of convergence. This is important. We say that the algorithm is at least of a linear order of convergence if the following holds for a constant c less than 1 and a natural number capital N. The difference between the n plus 1's solution and x star is smaller or equal, as a norm, than c times the difference in the nth step, and n being larger or equal than capital N. Now the same thing is given for the order of convergence if it's quadratic. Then we have a constant c, and we take this difference, which is supposed to be very small, to the second power. So we square it, and then we have a quadratic convergence order. Obviously, quadratic is faster than linear, and you can go on from there. So convergence of order 3, of order 4, is then better than quadratic convergence. We could also distinguish the local versus global convergence. Now, you know this probably from high school. If you are looking for a minimum of this function, it might be that you actually end up here, and this is a local convergence if we are only looking, let's say, at this area, and this is the global minimum. And as soon as we have restrictions, for example, if we only look at this area, then of course we don't have a minimum in one of those valleys, in those function values, but actually the minimum is given by the intersection with one of the restrictions. So convergence of an iterative procedure can actually depend on the start value. And if the convergence of an algorithm is only given when the start value is within a possibly small interval around the intended solution, we speak of local convergence. If it's irrespective of the starting point, then we call it globally convergent, and obviously global convergence is always better than local convergence. One example, Newton iteration. We are looking for the solution of a nonlinear equation, and we'll discuss this later on in detail. And this is, for example, given by the Newton iteration. So it's given by xn plus 1 equals xn, the previous solution, minus f of xn divided by the first derivative at xn. And we can calculate a root of one of the polynomials we've used before, and as a starting point we choose x0 equals 7.5. To do this in MATLAB, again we are using our slightly disturbed polynomial. x0 is 7.5. Polyder is the function that gives us the coefficients of the first derivative of this polynomial. x1 then equals x0 minus the value of this polynomial, polyval, p1 at x0, divided by polyval of p1 bar, that's the first derivative, at x0. We calculate this, we get 6.97, second step 0.0009, and now if we write it in a format that is long, x3, after just 3 steps, we have a root that is 7.000001, so sufficiently accurate. Now, after just 3 iterations, we get a relatively good approximation of a root. But note that the Newton iteration, also sometimes called the Newton-Raphson algorithm, is locally convergent. If we had used a different starting value, we would have probably found a different root. We have 8, 1, 2, 3, 4, 5, 6, 7, 8. So it could have also diverged to a different root, or it might not have converged at all. That's one thing to keep in mind here. Okay, and last but not least, I want to show you a very simple example how you can use all these very simple tools in some motivating examples from finance. So let's start with the cash flow stream of what is probably a very simple coupon bond. 0.8888 so this is an 8% coupon bond with a maturity of 2 for 5 years. So we can write this as a vector CF, and now we want to calculate the present value of this, and we call this PV. It's a function. It gives us the output PV. The function is called myPVvar. It has as inputs the cash flow stream vector and an interest rate R. And now we first get the number of periods, n, as the length of this vector. We predetermine the set of discount rates, 1 dot dash 1 plus R dot hat 0 double point n minus 1 in brackets. And this means that we don't use the vector multiplication, but we actually perform all these calculations element-wise. So all of these elements of this vector are divided by 1 plus r element-wise and not the scalar product. So this is why we're not using hat or dash, but we are using dot, dash and dot hat. And then dot, on the other hand, is the scalar product, and we just take the vector CF and the vector of discount factors, and this will give us the present value. Now in the next step, we are going to determine the internal rate of return. For this, we assume that the series of payments nominal value is 100, and as you probably remember from your Finance 101 class, the internal rate of return is given as this sum of the discounted cash flows set to equal 0, and then we'll have to solve for r. Now this is a higher order polynomial, so that's why we're using the function roots here. So let's assume minus 100 8888108. This is our cash flow, and because MATLAB writes down the polynomials starting with the coefficient of the monomial of the highest order, so it's actually x taken to the 6th power plus x taken to the 5th power and so on. We have to flip this vector CF from left to right. That's what flip LR does. And then we take the roots, and as a solution we get 0.9259, and for complex solutions we can disregard here because we are looking for one interest rate and thus one discount factor. If we convert this to a discount factor, we can actually see this gives us 8%. Now, if the price is 100 and we have 8% coupon and this is our bond, it's trivial that actually we get a discount rate that is equivalent to 8% internal rate of return. If we were to change this price, let's say to 98, then of course we would get a different internal rate of return. Well, you can try this out at home. Now, one could think of just taking the results whose imaginary part, so the complex numbers, is exactly 0 as we did here. In this example, it worked. However, in some cases, MATLAB creates some problems. For example, if we were to use x minus 100, so it has a triple root at 100, what we get here is 100, 100 minus something very, very small in the complex numbers, and plus the imaginary unit times something very, very small. So actually, we've mistaken this triple root at 100 in the real numbers for 100 and two complex numbers. So in this case, the triple root is misjudged as a single complex 0. Yeah? So one has to be careful when just saying, okay, we only have one real solution, let's just disregard these 4 solutions. Might actually be that MATLAB is still doing some sort of numerical mistake. Okay, so enough about the introduction and these motivating examples, and in the next video we'll start with portfolio theory.